Hey guys, welcome back to OIC Chris, where it's never too late to have an OIC moment. So today I'm going to be doing the next question for rates of reaction for the May-June 2021 past papers. So it's question 6. If you guys are enjoying the videos and finding them helpful, please consider subscribing to the channel. Please leave your comments or questions down below and I'll get back to them as soon as I can. So without any further ado, let's jump into the video. Okay, let's have a look at question 6. So question 6 says pure hydrogen iodide gas, HI, of concentration 1 mole per decimeter cubed is sealed in a 500 centimeter cubed container at temperature T. The reaction reaches equilibrium according to the following balanced equation. Okay, so 6.1 says the definition of chemical equilibrium. Okay, so that's just the definition. You guys need to learn. I'm not going to spend time on that. 6.2 says the graph below shows the concentration of the reactant and product varying with time during the reaction. Okay, so we can see there we've got a graph which is decreasing, which is y, and we've got another one that's increasing. Note the dependent and independent variable. We're dealing with time and concentration. So let's have a look at 6.2.1. It says which of the curves x or y represents the change in concentration of the products. Okay. Now, remember with the equation that's given over there, we're decomposing HI into H2 and I2. Okay, so whenever we have a reaction that takes place, your products are always going, your reactants are always going to decrease as the reaction takes place, and the products are always going to increase. Okay, so looking at that graph over there, we can see that graph X is going to be increasing. So X is our products. Okay, it asks for an explanation, and you can see that between T of 0 and T equal to 6 minutes, okay, there is an increase in concentration. Therefore, X has to be our products, okay, because now Y is decreasing, therefore Y is our reactants. Okay, 6.2.2 says, how does the rate of the forward reaction compare to that of the reverse reaction at T equals to 4 minutes? Okay, now, just because the two graphs, looking at that graph there, just because the two lines cross each other does not mean they equal. Okay, please note that. So, if we have a look for our products, the rate of reaction for forward, okay, you can see we started at a higher concentration of X, okay, whereas for the rate of reaction for reverse, okay, we started at 0. So start was at X, finish was whatever it was at T equals to 4, let's call that Y. Okay, but we can see that X is greater than Y, and we can see that X is greater than 0. Okay, which means the rate of the reaction for the forward has to be higher than that of the reverse. So just going back to the question, how does the rate of the forward reaction compare to the reverse reaction? Okay, so because we started at a higher concentration of X, okay, if we take the difference of that and then we work out the rate of reaction, you'll see that we'll have the forward reaction being higher than the reverse reaction. Okay. Now, 6.3 says the equilibrium constant Kc for this reaction is 0.04. Okay, so that's very low, which is not really good. At temperature T, calculate the number of moles of iodine present at T equals to 6 minutes. Okay, so note that just by looking at the graph again, at T equals to 6 minutes, we have equilibrium reached. So the minute you see Kc, you should be thinking of your Rice tables. Okay, so they've given us the Kc value. We want to know the number of moles of iodine. We know that Hi is 1 mole per decimeter cubed, and they've given us a volume of 500 centimeters cubed, which is 0.5 decimeters cubed. Okay, now remember, moles is equal to concentration times volume. Okay, so this here is just your concentration, and this here is your volume. Okay, so setting up our Rice table over here, we have the ratio for our reaction to 2 to 1 to 1. Okay, now our initial moles please note that this is the moles before the reaction even starts. So before reaction starts. Okay, unless specified otherwise with anything else, your products, you're not going to have any products. So these are 0 and this is 0.5. Okay, now let's have a look at the change. This is where your mole ratios come into play. So this is a change of 2x. We don't know what the change is. And because this is a 2-to-1 ratio, that's 2. And then this will just be a change of x over there. Okay. Now when we reach equilibrium, it will be 0.5 minus 2x, okay, and this will just be a quantity of x because we started at 0. Okay, so now our concentration, remember our volume is 500 centimeters cubed, which is 0.5 decimeters cubed. So this is just going to be 0.5 minus 2x all over 0.5. This will be x over 0.5, and this here will be x over 0.5. Okay. Now, they've given us our Kc value, so all we have to do is solve for x, and we'll know what the moles of iodine is. So our Kc value was 0.04. Okay. Now when we're filling it in, remember Kc is always products over reactants, and you have to take your number of moles into account. Remember, you square the concentration, or you cube root, or you power of 4, whatever your mole ratio is, you have to put in your exponents. Okay. So for this one over here, our products is the concentration of H2 and I2. Okay, the mole ratio is 1, so the exponents are 1. And here we have the concentration of HI, and that has a mole ratio of 2, so that's squared. So this can be 0.04 equals to x over 0.5 multiplied by x over 0.5. Okay, and that's all over 0.5 minus 2x all over 0.5, and this whole thing squared. Okay, now if you go and sort out the algebra and you square everything out and then you work it out, you should get an x value to be 0.071 or 0.072. Okay, so more or less in that range, and this is your moles. Okay, so that's how we go about doing the Rice table. Now let's have a look at 6.4. So 6.4, another graph is given. So they say the graph below shows the rate of the forward and reverse reaction for the with the change of time. Okay, so the forward reaction is a solid line, the reverse reaction is a dotted line. We can see it's the rate of reaction against time. Okay, note that at 10 minutes there's a spike. So let's see what they tell us here at 10 minutes. It says the temperature of the container is increased at t equals to 10. Okay, so that's your disturbance from equilibrium, was the increase in temperature. So now they ask which reactions shows an increase in the rate at t equals to 10. Choose forward, reverse, or both. Okay, now please note that looking at the graph quickly, we can see that at t equals to 10 there was a spike at 10 minutes due to the change in temperature for the forward and the reverse reaction. So therefore the temperature affected both of them. So the answer for 6.4.1 is going to be both. At 6.4.2 it says is the heat of the reaction delta H for this reaction positive or negative? Fully explain. Okay, so note that we changed the temperature at 10 minutes. Okay, and because we changed the temperature at 10 minutes, the forward reaction and the reverse reaction were changed. Okay, but let's have a look here. By increasing the temperature, okay, we favored the endothermic reaction. Why? Because by increasing temperature, we've increased energy into the system. Okay, now looking at this, since the forward reaction increased, so forward increased, okay, this means that the forward reaction needs to be endothermic. And therefore, because the forward reaction is endothermic, looking at this reaction, okay, we always know that endothermic reactions have a delta H which is always greater than 0, okay? So therefore, delta H is greater than 0, making it positive. Okay, if it was exothermic, delta H would be negative, and therefore this would then be delta H is less than 0 if it was exothermic. Exothermic. That brain lag there. Okay, so this would be the case if it was exothermic, but we can see that the endothermic reaction was favored because there was an increase in temperature, so therefore delta H needs to be positive. Okay, that's how we do this question. Okay, if you found today's video helpful, then please consider subscribing to the channel. Please leave a thumbs up on the video as well if you are enjoying the videos. If you have any questions or comments regarding the video, then please leave them in the comment section down below, and I'll get back to them as soon as I can. Remember, it's never too late to have an OIC moment.